So I'm going to go over, I call this the basics of quantum computing, but it's really not even all that. I just, again, because I know it's a mixed audience in terms of background. So I just want to give you just a way of thinking about a couple of things here. So as I said, I am not a physicist, all right? Which means that for close to 60 years, I never ever said the phrase wave function. And I managed to live a happy life. So therefore, if you were just looking at the theory of quantum computing, right, you can, with linear algebra and complex number theory, and about 3 seconds worth of probability theory, you know, at least have an idea of what's going on, and you can represent things mathematically. And that's okay, people approach things from different perspectives and so forth. But we do have trouble explaining really how a qubit works. And I will suggest to you that I don't think anyone in the world explains well exactly how a qubit works, so that your average person on the street will know what you're talking about. Right, so they kind of get 0 and 1 classically, okay, they kind of heard that, right? Although I will tell you, even computer science students, so again, you know, I'm speaking, 1, I know Waterloo is here. 2, I okay, but you may be surprised that many computer scientists do not learn much about circuits and computer architecture and things like this. They enter in at a very high level now, like programming level languages and all, right? That's lost. Now, I'm old enough that I saw that, okay? So therefore, kind of understanding this, and when you're talking about quantum computing, you have to be very careful to say, oh, well, it's sort of like a classical circuit, but it's different in this way. And the person says, I don't know what a classical circuit is, but thank you for trying to explain something to me, right? And things like that. So, therefore, this idea of a qubit and what it really is, or at least getting a sense of the power of it, we've been trying to come up with some ways. And then this is not recent by any means. This is called a Bloch sphere, B-L-O-C-C-H here. And it's a way of representing a qubit. Now, a single qubit, more mathematically, lives in a two-dimensional complex Hilbert space, which basically means a vector space with a norm. So here I'm just going to go right to the math. Okay. Now, because it has two complex values, you would therefore think it is a qubit lives in a four-dimensional real space. However, you can make a couple improvements on this, one of which is restricting the actual values the qubit takes on to being essentially the lengths of the qubits are 1 as they exist in the vector space. And the second one has to do with if we are trying to project that space now, which is now three-dimensional, onto the surface of the sphere, we can get rid of another dimension because we don't care about extra rotations, essentially. So what we will therefore do is say we are going to think of a qubit as living when it's operating on the surface of the sphere. So we're not just going to keep ourselves to 0 and 1. When a qubit is operating, when you turn it on, when you turn the on switch, it will take on values that are living on the surface of the sphere. And therefore the operations are a certain set of things you can do to points on the sphere that, first of all, move them onto the sphere, so they're preserving the length, but they're linear operations, so-called unitary operations. So you go from a basic zero-dimensional situation, 2 points being 0 and 1, to a qubit which is operating in a two-dimensional space. That's the main thing you want to say. And so what I've written down there is a little linear combination. So think of what I'm calling, bar 0, angle, bar 1, angle. They sort of look like 0 and 1. We'll call them 0 and 1. Do not think of them as the numbers 0 and 1 here, but think of them as basis vectors in a two-dimensional space, complex space. A and B are complex numbers. Okay. they have additional restrictions and so forth. So qubits live when they're operating. They're just getting moved around, right, and different things. Those are the operations. You can flip them. So to think about that a little bit more, we are going to arbitrarily label the North Pole as 0 and the South Pole as 1. All right? So flipping it, just as we might do in classically doing a not operation, so not 0 is 1, not 1 is 0. So there's an operation called X-polygate which flips 1 and 0. But there are many other gates, and that's pretty much where the resemblance stops. All these operations are invertible as well. Now, there's a very special thing that happens beyond what the actual gates are, which is measurement. So we start with a qubit, and the value is 0. And then we do something to it, and then we do other things to it, and multiple other qubits here. I know I'm waiting my answer. But when we measure it, and here I want you to be thinking about it living somewhere on the surface of the sphere. We're saying to the qubit, you must decide, are you going to go to the North Pole or the South Pole? And you can't say, I don't want to. You must go. All right? That is measurement of what happens here. So you would tend to think, well, the things below the equator, odds are they'll probably go down. Right? If I say choose, if you're in Brazil, choose, you're going to go to the South Pole. Right? You're thinking of it as the Earth in this way. However, anything that is not actually the South Pole has a little bit of a component which is towards the north. Right? And anything which is at the North Pole has a little bit of a component which is toward the south. So if we think of these as probabilities, I'm skipping over the actual mathematical representation. In fact, unless you are at the poles when they measure you, you might go north or south with some probability. What gets interesting is if you're on the equator. So if you live on this equator, and I say, choose, are you going north or going south? It's 50-50. This is quantum randomness. And as you can see, there are a lot of other values that can choose where you go there. So in any case, this is the, for some more technical audience, a few ideas of how to think about what qubits really are if you don't want to get into the physics. You can start here. The linear algebra comes in because of the unitary transformations. Now, one of the things with qubits that's really special is that when you add one qubit, you essentially double the computing power, in the best case. In the classical case, to double the computing power, I have to double the number of transistors. So I need a chip that's twice as big, right? Which plays into Moore's law, right? So whether Moore's law is dead or sleeping or whatever, right? Moore's law said roughly every 2 years, it gets twice as fast, twice as small, uses half as much memory, right? So this is the notion of getting twice as fast because we have twice as many transistors in the thing here. But here, and this is a 16 qubit device, one of the ones that we made here, you add one additional qubit, and the power of it, whatever this means, right, is twice and twice. So now I'm going to belabor this point really slowly here. Now I'll say it quickly, but in terms of slides. And again, if you're mathematically oriented, this is trivial. All right, so we're going to talk about exponential growth. We have one qubit, as I told you before, lives in a two-dimensional complex vector space, so therefore we have two coefficients of our standard basis elements, A and B. So for a single qubit, there are two pieces of information that can be represented, two complex values. Okay, so far so good. And that's pretty good, one qubit, two values. When I have two qubits, I can have four pieces of information. Right? And here, we've done a little bit of playing around with notation, and instead of just saying bar 0 angle, now we have some additional things like bar 0 0 angle. We have all the possible combinations of zeros and ones. So here the question comes in, okay, we We had 2, and now we have 4 pieces of information. When we do it again, do we end up with 6? You know, do we add 2? Or do we multiply by 2? And of course, the title being exponential growth, right? When we add a qubit, third qubit, what's happening with the mathematics, and this is a tensor product. That's what's actually happening when we go from 2 basic states of 4 to 8. You can see the number of combinations are going up multiplicative. So 3 qubits, the values live in an 8-dimensional complex vector space. When you talk to a non-technical audience, you will hear them refer to exponential growth. I will tell you that means they think really, really fast. They have no idea that it means like this. Right? It could go just like this, but really fast. You know, big slope and things like this. This is literally exponential. Did I make a typo? Yes, I did. You're the first one to discover that out of hundreds. Yes, H should be 111. All right. Thank you very much. And of course, so to the end here, we have 2 to the nth basis things. And that's why, going back to our caffeine example, right, we had 10 to the 48th, but when we had 160 qubits, that's 2 to the 160. That's where we get that information. So those bits are represented as coefficients, simple coefficients. So the largest computer, as I said earlier, is a 50-qubit machine that we have, or the largest machine that we have is 50 qubits. And so 2 to the 50th is that number that represents how many pieces of information. It's the dimension of the vector space of all those qubits. And by the way, this is where entanglement comes from, mathematically. This notion of tensor product and entanglement is how it's tied together. So when we get up bigger than this, so if you remember a little earlier, we were talking about sucrose and we were talking about penicillin. So sucrose required 274 qubits to represent the energy state. Penicillin required 286. Well, oddly, when we get to 2 to the 275th, that's more atoms than there are in the observable universe. So a quantum computer with 275 qubits, when it is operating, can essentially work with data that has more components, if you will, than atoms in the observable universe. How does this work? What's your rational explanation for why this magically works out? I've shown you some math, but the math does not translate, right? Well, it translates, but just having the math doesn't mean you can implement it, right? So how does a real quantum computer, even at the caffeine level, possibly access that much information? We don't know. This is quantum mechanics. This is why quantum mechanics is so weird. And there are religions that have been started over trying to explain this great notion of, and are we operating across multiple universes? And there's a lot of good weekend reading and weird science fiction about what this means. It does seem to work, and so we will take advantage of it. So hammering again for a moment on the number of qubits, we use this idea of quantum volume. So quantum volume, and volume, we want to make you think of dimensions. Right? There are multiple dimensions to talk about how powerful your quantum computer is. Yes, number of qubits, but error rates, the error rates between them, coherence time, your readout fidelity, all these different types of things go into it. It turns out this question of saying how powerful is your quantum computer is really tricky. It's not obvious at all. I mean, we used to, if you were in the 90s, for example, your processor chips were getting faster and faster, and so more powerful. You had more memory, powerful. It's really kind of tricky because of the way qubits work together, this notion of entanglement, right? depends on the topology of your chip and things like this. So we need some way of comparing, right? Quantum volume is pretty much a stress test. Right? I sometimes wonder why the computer isn't in rubble on the floor by the time you're done testing. It's so much work, you know, to actually go through this. We're hoping to standardize something like this ultimately, so that you don't have to rely on the media saying, you know, these qubits, those qubits, whatever, to actually be able to do this. Now, to that end, we publish the operating parameters for our chips. So if you go online, and I'm about to tell you about the Ibm Q experience, you can look up and you can see the specs on, you know, the error rates of the quantum computers. We're the only ones that do this. A few other people publish this. You know, look at this great qubit; it's doing really well. Well, what about the other 50, whatever they are? Right? Well, we don't want to tell you about that. Things like this. So as we move forward, there's all this excitement, right, about what's going on with quantum. You're going to have to be ready to stand up and be measured. And so this also means, you know, from a startup perspective, depending on what you're doing, your algorithms, your implementations, people are window shopping. You know, large banks, they're window shopping. You know, they may be interested in talking to you. Trust me, you're talking to 4 other people at the same time. This is significant. So the Q experience is something we put quantum computers on the cloud in May of 2016. And this was a very non-IBM thing to do, which is to take this experimental research technology and put it out there on the cloud. And we had no idea how many people would use this. But we had solved some problems and we wanted to make it available to people to just figure this out. I hope I've given you the impression that quantum computing is new and strange enough. It's going to take time to learn how to actually do things with this. And I don't mean the most technically oriented people, right? I mean, there are millions of software developers out there. Getting that large community able to start doing some things. All right, so May 4th, 2016, we broke 100,000 users last month, which is more than we ever thought. And frankly, this is why people are noticing. So use this as a proxy. I mean, we're very pleased for our system. But use this as a proxy for interest in quantum computing. If at this point, 2.5 years later, we had still had 75 people using it, right? I would not be investing in any startups, right? I mean, just again, proxy, right? But nevertheless, right, we've had 100,000 users that run over 6.6 million experiments. Many papers written by non-IBM scientists have been written. It's used in many colleges and universities and things like this. We fully appreciate this is the first stage, right? We're the first ones to get this out there. We're trying to build on this. We're always evolving this. So again, use this as a proxy to show interest. So when you go to the Q experience, you essentially have 2 computers you can use. You can use a 5-qubit machine, and you can use a 16-qubit machine. This is a drag and drop environment we have for a 5-qubit machine. We call it a composer, 5 lines, you can use it for composition. And you drag and drop gates. And so these are quantum gates, and what you can do is you can bring them over, and you can set them up. Some are single qubit. H is a Hadamard gate, X is the flip gate. I told you about that before. There's a C0 gate, which is the plus with the line, which operates on 2 qubits. And then this is measurement, which is, and I told you, you must decide whether you're 0 or 1. So once you set this up, then you can say, well, run it on an actual quantum computer or simulate it. So you have your choice. People often do both, right, depending on what they're doing. While they're debugging, they simulate it. If they're trying to learn about quantum computers, actual quantum computers, then they run it on the machine. And I do understand there's a certain novelty to running something on an actual quantum computer, but that's okay. So that's the 5. All right, so let's just park that for a moment. This sort of interface gets unwieldy with a larger quantum computer. It's JavaScript under the covers. That should be more than enough to say it gets on the middle. What about if you're actually coding? And so we have an open source platform called QuizKit. It's available under the Apache 2 license. It's on GitHub. We're now up to version 0.6. You can go, you can download it, and you can program that 5 or the 16. You only can access the 16 via QuizKit, by an actual program. And so tonight you can go home, you find the Ibm Q experience, you download QuizKit, and you can be coding real quantity. As we have evolved this, we have restructured it. At the 0.5 level, we broke it into 4 pieces: Aqua, Ignis, Air, and Terra. Yes, it's got that earth, wind, and fire thing going. But in Latin, so it's better. Terra is the foundation. Terra is the level that operates on circuits and interfaces with the simulators and the hardware, the backend. That's available. Aqua is the higher level libraries. And so there are the standard quantum algorithms that are implemented, and also interfaces and algorithms for chemistry. Recently we've been doing some things on financial services. Not quite yet available. Ignis is going to be for error correction, and then Air is for the simulators. Focus more on the simulators and emulators, as well as some of the binding as well. So Aqua here, pip install it. The whole QuizKit is Python 3, so you just do what you do with Python 3. We have complete instructions, we have videos, we have everything you need. If you are a chemist and you work with things like Gaussian and Psi4 and whatever, we support most of those packages. And we do it in a rather novel way. We are not trying to re-implement everything in chemistry in yet a new library. We're saying chemists have an existing workflow. How can we extend that to use quantum computers or programming? Financial services people have a particular workflow. How can we extend the tools they use to work with quantum computers, as opposed to saying we have to rewrite everything? So that's Aqua, and then Terra, as I mentioned as well. Commercializing. So that was the free side. We also have something called the Ibm Q Network. So we will keep the 5 and the 16 qubit machines up there, largely for experimentation, education, things like that. Although quite a few people have written papers, the newer machines will be made available through the Q Network. So this is a very early way to understand what the applications will be. So imagine you're a large company. You think there might be something here. You want access to our scientists, to our latest hardware. You make some sort of agreement with us through the Q Network. So that's the idea there. But what we're also doing is hubs. So IBM, the total is 400,000 people. IBM Research is 3,200 people, but they don't all do quantum. And so we needed the ability to scale. And so we need to go out to other organizations, typically universities, and say, you have quantum expertise, and you would like to work with startups, companies in your region, and so forth, but you don't have a quantum computer. You'd like to use our quantum computer capability. So that's what a hub is. So they get all of the computational bandwidth, if you will, from us. We have direct partners, and then we have somewhat lighter call members. This is the current list. Well, it's actually not quite current. There are 1 or 2 others that have been added. But you get the idea that most of the hubs are universities. This gets updated. We're always working with people. The most advanced hub is Keio in Tokyo. There are 4 commercial partners with them. And we have a very large group of startups, some of which I think might be pretty cool. So let's talk about IBM Q. We did a count, and there are roughly already 100 quantum startups around the world. That's a lot. So do your homework. Okay. we started with these 7 or 8 down here. We've got a few other ones. We're going to be announcing more, and that's why these are just slightly in gray right now. Fundamentally, we're interested in having people work with us in the Q Network as a startup. But really, you got to kind of use our stuff. It's not a co-marketing situation where, you know, just to be very honest, you get a press release with Ibm on it and you don't talk again. Okay? So either you're using something like QuizKit, you're building software, you're building your applications on top of that foundation, or you're more hardware oriented or lower level software oriented in the stack, and it might be something you might be interested in using or working on. But if you're just a random startup who just somehow wants to be, that's not for you, right? And we wouldn't bring in people that way. It is a nice program. We are extending it. We're changing it a little bit for next year, basically making it a little bit more intense. All right, so I want to end here. And again, I appreciate you staying a little later in travel problems here. I just want to talk a little bit about quantum and academics. So, in universities, there are really 2 parts here. Waterloo, this whole area, as I said before, is just exceptional. But there are thousands of universities and colleges in the world that don't have the access that you do. There are thousands of experimental physicists who are not building quantum computers, all right? But they want access to the machines. So they want to do their research on cutting-edge quantum computers. So that is one reason to work with us. We have a variety of ways of interacting for research. Even to the point of, we published last month what we call Open Pulse. So a quantum computer, or our quantum computers, are programmed at the lowest level using microwave pulses. Different pulses generate different gates and so forth and things like this. But you could basically build your own gates. You can experiment with how they operate. This allows you to actually go in at, again, the lowest possible level and create your microwave pulses and have them on our hardware. So this will be exposed in the API fairly soon. And then education, of course. So it's always seemed clear to me that we have to go after university education and sometimes even advanced high school education. Because remember what I said before, 3 to 5 years from now, maybe we'll have these examples, people will be hiring, but people will still be very much, and for decades, trying to figure out what is this stuff good for? How does it work with classical computers? What better place than to go to the universities? Now, I used to think, oh, more people should have entire courses of quantum computing. Well, that can be very difficult in many universities. So the better universities ought to do that. It's interesting to know where they put it. Oftentimes it's in physics or engineering, right? And not, let's say, computer science. Generally, across the board, computer science very definitely is lagging engineering and physics in education related to quantum computing. What I'm now thinking, although that is a nice thing to have, certainly we'll take it, and we have many people who are using the composer for education, the QuizKit to actually do things. I'm thinking it makes a lot more sense to start augmenting existing classes. So if you teach a class in classical computer architecture, take 2 lectures and talk about quantum computers as well, right? You have to start sneaking it in there, because eventually people will like the ACM and will make it part of the formal curriculum. So there are lots of areas, and I will end by just saying, so I took linear algebra as a freshman in college many years ago. As I said, I was a mathematician, so that's great. I was not looking at what I was doing, saying, what is it good for? You know, that was a theoretical mathematician. That it existed was fine with me. And I remember that there was this one particular type of matrix factorization in it, and we went through it, and I thought, this is very nice, this is how you do it. But again, I didn't really know what it was good for. Last year, I finally discovered what it was good for, and it's something in quantum mechanics. So it only took me 40 years, So there's a lot you can learn about quantum. It's an ongoing type of thing. If you are new to it, it's strange. You will learn something and you will wake up someday and realize what you thought you understood was completely wrong. But you'll have much better insight about something else. So it's a long process, and that's why we have to devote time to education. Okay, so thank you very much.
Thank you so much for the great talk, Dr. Zucker. Thank you. If we can have you a few more minutes, and if I can invite Dr. Malko and Dr. Peter Videk